to prove equation 1, so one first writes this quantity in Schwinger, in what is called Schwinger parameterization, which is given by this. It's basically using the fact that if you integrate ds0 to infinity to the power minus s times a, then the result is e to the power minus s times a divided by minus a between 0 and infinity. At infinity to the minus s a will be 0, and therefore it will be 1 over a. At 0 it is 1. So so this is called then perform a change of variable from S1 to Sn to alpha, which is given by sum of all these s's, and alpha k, which is given by sk over alpha k running from 1 to n minus 1. So I have n variables S1 to Sn. I'm changing them to another set of n variables, alpha k, n minus 1 variables, and alpha, right? Then show that this integral ds1 to dsn 0 to infinity can be written as d alpha 1 to d alpha n minus 1 0 to infinity theta 1 minus sum over k equal 1 to n minus 1 alpha k times d alpha alpha to the n minus 1 0 to infinity. Sorry, this is 0 to 1. Okay. Now the limits on alpha 1 to alpha n minus 1 is because of the following reason, that since each sk is going from 0 to infinity, if sk equal to 0, then alpha k equal to 0. But if sk goes to infinity, then alpha also goes to infinity, because alpha has sk sitting in the sum. So if sk goes to infinity, alpha also goes to infinity and becomes 1. So each alpha k will have a range 0 to 1. Now there is one more condition here, which is given by this condition, and that comes due to this following fact, that if you take sum over k 1 to n minus 1 alpha k, then that is sum over k equals 1 to n minus 1 sk divided by alpha, which is sum over k 1 to n minus 1 sk plus sn, right? That is what the transformation, the variable change is. Now If Sn goes to 0, then this sum, Sn goes to 0, then this sum becomes 1. And if Sn, so there are two limits, there are two limiting values of Sn, 0 and infinity. If it is 0, then it is 1. If it is infinity, then it is 0. Okay, so therefore this sum should vary between 0 and 1. And that is what this condition means, where theta x, definition of theta x is that it is +1 for x greater than or equal to 0 and 0 for x less than 0. Okay, so this I just argued that I just argued that this quantity is in 0 and 1, and that's why we have this theta. Okay, now given this, therefore we get to the result, we get to the following conclusion, that 1 over a1 to an is given by times exponential. Now I'm writing this e to the power minus skak, this factor. So the first k equals 1 to n minus 1, sk will be replaced by alpha times alpha k, and then Sn will be replaced by alpha minus sum over Sk, which is alpha times alpha k. So therefore it will be minus alpha sum over k equals to 1 to n minus 1 alpha k ak minus 1 minus k equals 1 to n minus 1 alpha k times an. So this is, this alpha times alpha k is sk, that is sk ak, and this is alpha times this is alpha is Sn. Sn, as I said, is alpha minus sum over k sk, which is alpha minus sum over k alpha times alpha k. So alpha comes out. So this alpha times alpha k is sk, so this is sk ak, and this term is supposed to be Sn an, and Sn is as I said, alpha minus sum over k sk, but sk is alpha times alpha k, so alpha minus alpha times sum over k alpha k, so that is 1 minus sum over k, so there's a plus sign here. Okay, now let me call this next part of the manipulation is, let me call this x. Okay, then, and okay, sorry, I have to explain this symbol. This is integral with the theta function. Okay, that's what that means. Then what you can do is to write this same expression 0 to 1 d alpha 1 to d alpha n minus 1, and then you have alpha to the power n minus 1 e to the power minus alpha times x, and it's a standard trick that you can write this factor but as a derivative with respect to x. So each time you take a derivative with respect to x of this exponential, you bring down a factor of minus alpha. So you write del n minus 1 del minus x n minus 1 of integral d alpha e to the power minus alpha x from 0 to infinity, right? This is what it means. Each time you take a derivative of this with respect to minus x, you bring down a factor of alpha, and you do it n minus 1 times, so alpha to the power n minus 1, right? Now this integration, as I said earlier, for the Schwinger parameterization is nothing but 1 over x. So that means this derivative acting on 1 over x. So if you calculate it, del n minus 1 del minus x n minus 1 acting on 1 over x is x, you replace x by minus x by y, del y n minus 1 and that's the result is minus 1 to the n minus 1 times n minus 1 factorial divided by y to the power n. So if you take a first derivative of 1 over y, you get 1 over y squared. So number of derivatives, the number of derivatives will become the power of y. The power of y will be number of derivatives plus 1. If you take one derivative, you get a y squared, two derivative, you get y cube. Each time you do that, you get an extra factor of minus sign, minus 1, because it is 1 over 1. It is in the denominator. So that's why you have minus 1 to the n minus 1. And you also pick up this factor. So first derivative will give you 1 times y to the minus 2. Then the second derivative is 1 times 2 times y to the minus 3, and so on. So that give you a factorial of 1 minus 1. So that's the result. So this minus, so this is same as minus 1 to the power n, and multiplying y to the power n will give you x to the power n. And my n minus 1 factorial is nothing but gamma n. So that is gamma n, and this is x to the power n. So that is the result. Therefore, a1 to an, this quantity is written as d alpha 1 to d alpha n minus 1, 0 to 1. Then, so let me write this thing with the theta explicitly. So theta 1 minus sum over k equal 1 to n minus 1 alpha k divided by sum over k equals to n minus 1 alpha k ak plus 1 minus k equals n minus 1 alpha k an to the power n, right? This is what x is. So I'm writing 1 over x to the power n. So this is 1 over x to the power n. Now you introduce another alpha n to be same as 1 minus k equals 1 to n minus 1 alpha k. If you introduce that, then the same result. Okay, just a moment. The same result can be written as I missed a factor of gamma n here. So gamma n integral d alpha 1 to d alpha n minus 1, 0 to 1. Theta 1 minus sum over k equals 1 to n minus 1 alpha k divided by sum over k equals 1 to n alpha k a k to the power n. With this definition, this becomes alpha n, and therefore this is sum over k 1 to n alpha k a k to the power n. But now we take alpha, so this is not alpha n minus 1, so I include the integration over d alpha n as well. So originally I had that n minus 1, but now I'm putting another d alpha n, the same alpha n that I have introduced here, but that's an additional integration which is actually not there, so I have to fix it. So I put a delta function which equates alpha n to this, which means that this equation can alternatively be read as sum over k 1 to n alpha k equals 1 if you take this on the other side. So this is sum over k 1 to n alpha k minus 1. So that is the delta function. Now, once you have that, then in this expression, if you have sum over k alpha k to be equal to 1, because we have already, then it is guaranteed that this object will be less than 1, and therefore this theta is actually redundant. So this is actually redundant. So you can remove it, and that leads to the actual equation, actual result, which is this, where we have a gamma n and then n alpha integration, n integrations with dl alpha 1 to d alpha n each going from 0 to 1. We have in the denominator alpha 1 a1 to alpha n an and the delta function. So that is this the proof of the first result. Let me end this part here.